Guys. Okay, so hi everyone. Thanks for attending. My name's Jonathan, and the topic of my talk is going to be about the dark side of Winsock, which is essentially all the under-the-hood functionality that you have inside Winsock, inside the Windows TCP/IP stack, which unfortunately, even though it's there and it's publicly available, it is somewhat undocumented, and the only people to really use it are the bad guys, namely people who want to do rootkits, who want to do spyware, etc., etc. Now, I find myself somewhat inclined to start with the preamble here. This is not some type of vulnerability issue or not some type of any, zero-day exploit. So if any of you are expecting that, it's probably not the right place to be. What this is, however, is a discussion on functionality, which, like I said, is in there and is mostly, mostly the only really good uses, as you'll see, are the insidious ones, namely the ones that aren't really designed to happen. Things such as usurping connections, rerouting connections, connection monitoring, and et cetera, et cetera. Now, it is assumed that you guys have had some experience with Winsock before. How many of you have actually coded in Windows for Winsock? Okay, so as I was, I kind of suspected that. So we'll start with a brief intro that kind of has the nomenclature and kind of has like the basic terminology. So those of you who are fairly new to this will be able to sort of like keep afloat. And then we'll get into the code. Now, the code itself that I'll be demonstrating is all fully annotated. You've got that on the CD. On the CD, you have a PDF of my talk, which, contrary to other PDFs, it's not just the slides, it's also the notes pages. So you'll be able to have the full source code. Everything is there. Furthermore, my demo, which I'm going to run shortly, is based on a public demo, which is Intel's and Microsoft code. So it's like fully open source and nothing too new there. So we start with the introduction, and some of you may already know this, and I'm actually hoping most of you know this, but it's just like sort of like the basic terms we'll be using. So as you all know, IP communications are usually based over what's known as sockets. Sockets were something that essentially are meant to abstract sort of like what you'd have with file descriptors, only in this case it would be network descriptors. The idea is fairly simple. The application would open a socket and would just send and receive data as it would with any other file descriptor. This could be using receive, send calls, etc., etc. And there you'd also have some other APIs, which are essentially get peer and get adder info and so forth, which are meant to be socket specific and to enhance these descriptors so as to accommodate all types of TCP and UDP based needs. Now, the application itself is somewhat agnostic in the sense that for it is just another file descriptor. Those of you who may have some Unix background know that sockets and file descriptors in Unix are one and the same pretty much. So you can, you have the very same API. In Windows, what happens is that you have the Winsock, which I'll be describing shortly, which takes the sockets just a bit further and gets you a lot of added functionality. Now, the important thing to emphasize is that the application would read and write just with any other file descriptor. So what would happen essentially is that all the fragmentation, encapsulation, and getting the IP header and the TCP header or UDP, whatever it is basically handled transparently by the OS, which is really good news for a lot of application developers because they just work transparently and just don't care about whatever IP issues or TCP and so forth issues that might arise. Now, what I'm going to demonstrate to you works with pretty much all sockets of all types. It works with TCP, UDP, raw sockets as well, in case Microsoft hasn't crippled them completely in Service Pack 2, and also IPv6 sockets, which is really nifty. Now, the way it works is that Microsoft took the BSD model, which is your average libc type socket with all the rich API, and adapted it into something known as Winsock, which is basically Windows sockets. This went through several versions and revisions. We started with Winsock 1.x, which you're not going to see anyway because it's mostly like for Windows 3.11 and so forth. And Winsock 2 is basically your baseline today. That is to say, it's present in Windows NT, it's present in Windows 2K, 2003, etc., and of course your XP. Now, the major important issue with Winsock is that the migration from 1x to 2x added a host of new features. We're not going to be discussing those new features at length, but some of you may know that it provides for asynchronous calls and various function callbacks, which is really good if you're working in a multi-threaded environment and so forth. It works with overlapped I/O, namely getting more than one process to listen on the same socket. And this is going to be the topic of our talk here. It provides something known as an LSP architecture, which is the layered service provider. This is going to be a very key and instrumental term for us, as this is essentially the core of the talk. This service provider interface is essentially giving you the architecture to hook any Winsock call by any process, aside from certain system processes which bypass Winsock. We'll get into that in a second. But essentially, any Winsock functionality you wish. Well, it can be anything from get host by name through, of course, sending and receiving in sockets and so forth. Everything is pretty much hijackable in the sense that this is pretty much the equivalent of set Windows hook that you'd have for general Windows API functions, only specific for the Windows platforms. Now, this is really, really useful. And we're going to be talking about some of the legitimate uses, which, as you'll see, there are quite a few legitimate uses. However, we'll also see that the really important uses are those that are, so to speak, less useful for the good guys, and mostly sort of like the covert or the black hat oriented uses. Now, it's also important to say that, like I said, this has been out there for about 7 years now, pretty much. My first encounter with that was like 1998 or so. And it's really frightening to see that all this functionality is there. It's under the hood, so your applications are fully agnostic. They have no idea that this functionality is there, and yet spyware developers and other such application developers can pretty much inject whatever functionality they want, and the application is none the wiser. So, getting into detail here. This little illustration here shows you pretty much what the Windows networking architecture is all about. Some of you may find this a bit familiar. For those of you who aren't, I'll just run a brief sort of like review of this. So looking at this from several levels of abstraction here. Oops, wait a second. That's Microsoft PowerPoint running wild on me. So looking at this from several layers of abstraction, we can see the hardware down below. Now, no matter what hardware type you're using, whether you're using a wireless network or a wired Ethernet or even a modem, pretty much all your Winsock calls will eventually be rerouted over the hardware in a sort of device-independent manner. The miracle that does this is something called the NDIS driver, which is the Network Driver Interface Specification. That's sort of like an abstract driver for any type of interface. In Unix terms, some of you may be aware of the ifconfig and the interface configuration. So it's pretty much a port of the same idea in Windows terms. And the NDIS is essentially an abstract driver that works with pretty much all types of communication devices. These can be modems, these can be Ethernet cards, etc., etc. Following that, we have the TDI, which is a transport driver interface. That acts somewhat like a bridge, in the sense that you have calls from user space going into kernel space through this TDI layer. Now, in user space, you mostly have either Winsock 2 for 99% of the applications, or something known as NetBT, which is the NetBIOS over TCP/IP transport. Some of you who might be familiar with a // server, the SMB or CIFS notation, that's pretty much it. So aside from the workstation and server service, which are core components of Windows, pretty much any other application would go through Winsock. And that, of course, is what makes this all the more attractive to us. Now, as the applications go through Winsock, they are pretty much, they all work over the same API, which is the Application Programming Interface. And that is the API that you link with Winsock, or WS2_32.dll, and it gets you the functionality of the send, receive, and as well as a host of WSA calls, namely WSA async select and others, to name a few. Okay, so you have all types of applications. They can be your browser, your FTP, naturally your IMs, probably go over that as well, IRC, etc., etc. Now, this is sort of like the application type view that most programmers are familiar with. However, as it turns out, this is only half the picture. So if we try and look deeper, we see that we have this Winsock API layer, which is, again, the top interface. But we also see that we have a Winsock SPI layer, which is a bottom interface that is meant for what Microsoft defines as service providers. Now, the term service provider, like I said, is a key term here, because service providers are essentially either hardware types, namely, your network cards, et cetera, or they could be software types, as in software-type drivers, which are mostly user mode drivers. Now, this is really important since it gives you the full functionality of packet inspection and whatever you want, but at the socket level. So essentially, from an OSI model perspective, we're working at layer 5, which is really quite the improvement over other types of sniffers and rootkits, which generally operate at a lower level and thus confine you to a packet view. So here you can actually hijack a socket and not really wonder as to whatever the breakdown of the packets is, because it doesn't really matter. Now, essentially these providers are one of two classes. You have the transport providers, which, as the name would imply, work with the data transport itself, namely the TCP and UDP transfers, etc. And you have the namespace providers, which work with all the, get host by name, etc. Namely, if you want to look up any type of address, that address can be a NetBIOS name, it can be an SMB name, a CIFS name, etc. And this would imply, of course, that you need a mechanism to abstract that. And this is exactly what the namespace providers are all about. I'm going to focus on the transport providers because they are, of course, the sexier ones, in the sense that they actually get you to see some real data. Now, as the illustration also shows, all the providers would share the same API, the same top API, which is what I see here, what I marked here, as a transport SPI. That is the transport service provider interface. So whatever provider you're using, essentially all these providers must work pretty much the same way. Now, Winsock providers cannot normally be listed by applications, or at least they can be, but only if the application is actually aware of it. Microsoft has, as part of the platform SDK, which is part of the Visual Studio distributions, they have something known as an sporder.exe, which is a small executable meant to show you the service provider order, of course. And also it comes with a small DLL called sporder.dll. sporder.dll is a DLL we'll discuss shortly. It actually has the ability to not only show you the service providers, but actually shuffle them around as you see fit. And this type of shuffling around is exactly the hooking functionality. So going on to see a slight demo of what the service providers are like. Okay, so autocomplete is not cooperating. So you have the sporder.exe, which shows you all the available service providers here. Now, my display is particularly cluttered due to the fact that I have VMware here, which is pretty much all those global unique identifiers that you can see here, as well as another VPN solution, which opens up a sort of like a virtual interface. But the core providers that you're likely to see are the ones you see here. There's one for the infrared, which is ERDA. There's one for basic TCP/IP. There's one for UDP/IP. There's one for raw sockets. And there's two of them for RSVP. RSVP is a quality of service protocol, which is generally supported but never really used by Windows. Now, going into one of these, you can see that they essentially give you the complete information on the service provider, namely which DLL is actually the one that provides the functionality, as well as a bunch of service flags, provider ID, which is a global unique identifier, etc., etc. The important stuff here that some of you programmers might recognize are the address family, the hex value 2, meaning AFINet. There's also the socket type, which is sock stream, and there's a protocol number, which is 6. 6, of course, for TCP. And naturally, you'd have 17 or hex 11 for UDP. And so the way that works is at any time an application would request a type of socket to be created, which would be a sock stream, rather an AFINet sock stream and a TCP, essentially a TCP socket. What would happen here is that this call would be redirected over to mswsock.dll, where Winsock, or the WS232 DLL, is actually acting like a multiplexer. That is to say that it is one main interface under which you can have all types of various providers. Now again, this would normally be the case with your average Windows, and the more interfaces you have and the more applications you have, the more of those providers you're likely to see. As for the name resolution providers, these are the namespace providers. You have your basic TCP/IP, which is an interface to the DNS client service. You have NTDS, which is, of course, Active Directory. And you have network location awareness, which is something that, again, Microsoft supports but never really works. So you have all those. And now comes the important part. The important part is that you can have, over these service providers, you can have a functionality that enables you to chain your own providers. That is to say, not just add a provider, and by doing so, you're going to have to essentially make the application aware of that provider, but you can pretty much hook your providers and install something known as a provider chain, which is really an amazing idea. Now, the original plan behind that was to support all types of nice uses. Nice such as transparent encryption, such as quality of service, etc., etc. But the way that works is that most applications don't really use that functionality, and so it's just left there, but not really used in everyday terms. Now, the beauty of it is that you can chain any number of providers, and you can chain them in pretty much any order you want. That is to say that if you want to provide some encryption functionality, for example, or reroute everything, all types of data transparently over SSL or SSH or whatever other tunnel you want, you can pretty much install your provider and then bump it to the top of the stack. So any other application using the stack would essentially get directed to your provider first, and your provider would do whatever, and then follow down the chain, essentially progressing the API calls down the chain. Any questions thus far? Okay. So the way it works is that your Winsock, the DLL itself, has several functions which are exported. I'm going to try this, the dump bin demo, a bit clearer here, so you'll be able to see the font back there. So just looking through that, hold on, let me just get something done here. Okay, so what I'm doing now is I'm setting up the Visual Studio command line environment so I can show you the dump bin command. And the way dump bin works is, as some of you may know, it gives you the DLL and shows you all the exported functions or the imported functions and so forth. So what I'm going to do now is essentially look for an exported function list of Winsock and focus on the specific service provider interface. To do that, what we'll do is just do dump bin /exports, get the name of the WS232, and since essentially Winsock exports like on average about 100 and something functions, I'm going to use a command line utility of grep to isolate only those important ones for our discussion. So looking at that, you can see that you have these particular WSC functions. Now again, those of you who might be working with Winsock on a daily basis know that Winsock usually exports the WSAs, which are for the Winsock API. The WSCs you see here are essentially all about the service provider interface and so forth. Now, there's too many functions here to actually go over, but the ones of interest are essentially install provider and deinstall provider, which enables you to, of course, set your own LSP or remove your LSP, as well as install namespace, and for some weird reason, it's uninstall namespace, hinting that maybe this API was not really meant to be used because it's not really standardized in that sense as an uninstall and not deinstall. Now, all of these are also fully documented as part of the MSDN, but it's the kind of MSDN documentation that resides on like the 4th CD that nobody ever gets to because it's like so obscure in the back. Okay, now, as it so happens, okay, these functions are readily exportable and you can use them to do your own type of work, as I'll show briefly in a demo. Now, this SP order DLL is an additional DLL that, as I said, works for rewriting the service provider order. And as the example here shows, this is a dump bin of the SP order DLL, and you have write namespace provider, write provider order and write namespace order, which essentially enable you to shuffle around, as I've stated, and put your provider just in its right location. Now, a lot of spyware-aware applications, like adware and all types of anti-spyware, essentially look for that DLL, and if that DLL is present on your operating system, then it's bad news. Then they normally flag it as spyware and so forth. Probably the best example of that was Kazaa, the file sharing utility that has sporder.dll bundled in. So when you install Kazaa, you have this DLL somewhere on your system. Another interesting application to use this type of DLL is Google Desktop. I don't know how many of you use Google Desktop, but Google Desktop has probably its niftiest feature is that after you install it, whenever you go into google.com, you suddenly get your own desktop there. You have like the ability to search Google or to search your own desktop from the very same web page. Now obviously that kind of functionality would imply that Google has a mechanism in your machine that can intercept the calls to google.com and sort of like rewrite the page content on the fly. And that is exactly the functionality that I'm describing here. Namely, by installing their own provider and putting it in your machine, they can intercept the calls to Google, but they can, of course, do whatever they want. That is to say that if they're not really playing by the rules, they can do a lot of other stuff as well with your machine. But then I'm happy to see that not too many people use Google Desktop here, because that's kind of like shady. Anyways, so going over that, probably the most interesting API call would be the WSC enum protocols, which would be the API call that one would use as a setup to install their own provider. This, much like all the other WS enum functions, will enable you to sort of like go over the protocols that are already in place and provide for an enumeration of them. An enumeration, in our case, would be a pointer to an array of protocol infrastructures. Now, you have a fully annotated example on the PDF, in the PDF, so I won't really go into that. But the idea is fairly simple. Anybody can call this function and see what service providers are already there. And in many ways, this is pretty much the only mitigation against this type of attack. However, most applications don't really use that, and if anything, they would use the counterpart of this call, which would be the WSA enum protocols. And the difference between the A and the C is that the C can get all the protocols, whereas the A gets only the top layer ones. So if you're using yours in a chain, essentially you can remain hidden, which is of course bad news. So going over that, we have the enum protocols just to see which protocols are there, and we naturally want to build our own service provider. Now, building a service provider is really fun. It's really easy too, because as a baseline, you have the Microsoft Supply demo. So I happen to have this demo right here, and I'm going to work with the actual Microsoft code. Due to copyright restrictions, I haven't really bundled it or put it in a tar GZ for you guys to use, but it's fairly simple to just get this code from the MSDN and just work and do the same modifications that I did right here. So looking through that code, let's start with probably the DLL main would be a good point to start. So launching Visual Studio just so we can see this type of DLL, then our service provider is just going to be another DLL. So essentially it has to follow the very same conventions. That is to say it has to start with a DLL main, and the DLL main would work as pretty much all DLL mains work. That is, whenever an application would hook to us and would call us, we would get the DLL process attached as the DW reason. And so the way that works is whenever a process attaches, I add this little addition here, which essentially doesn't do much. What it does is it just opens up a file name. Okay, it readies a file name here with an sprintf, composed of sockdebug as a prefix and the current process ID embedded in there. The reason I do that is because once I'll do that and, of course, run my applications, you'll see that each application, as it uses Winsock, will generate this type of file on the root of the C drive. Okay, and what it does here is that it just opens the files and pops a message box, and you will be able to see that message box. That message box and any type of code that I run here is run in the context of the calling process. So while this is a somewhat innocuous example and just, only for demonstration purposes, I'll print out a lot of stuff, if I really wanted to, I could do whatever I wanted here. Essentially, I could load additional DLLs, as the comment says. I could decide that this particular process should not access the stack, and so forth. Now, to make matters even easier for the spyware people, this type of functionality can also be injected in the WSP startup call. The WSP startup, which is shown right here in the slide. So WSP startup is essentially the counterpart to WSA startup. Those of you who may have been working with Windows know that each Windows application, as it starts, as it launches its Winsock functionality, has to start off by calling this function, the WSA startup. And what it does is that it requests a certain Winsock version and requests certain capabilities. Now, the beauty of it is that most programmers just call WSA startup, check the return value, and naturally everything is just okay. However, these programmers are unaware that this essentially would call the WSP startup, which is our code. So in our LSP, what we're going to do is essentially implement a WSP startup, which will have our very own code in there. Now, looking at WSP startup, you can see that it has 5 parameters, as opposed to WSA, which has, of course, fewer parameters. The parameters of interest here are specifically the 3 last ones. We have the in parameter LP protocol info, which states what type of functionality the application expects. Namely, are we expected to perform TCP or UDP or any type of other service? We further have something known as the upcall table, which is by far the most useful parameter here, which will enable us to have an array of, essentially it's a pointer to an array of functions. And these functions are the already installed providers. So that means that if I want to hook, for example, send or receive, I don't really have to think about how I would implement send or receive, but rather I would implement them my own in sort of like a stub function, and later on just go on to call the upcall table. And the example will demonstrate that shortly. Finally, we have the only out parameter here of interest. The other one's really not interesting. The LP WSP data is really not interesting. But the LP proc table here is our procedure call table, and that is essentially a pointer to all our functions. So whatever functions you choose to implement, you can pretty much set in this big structure there, and just call WSP startup, and returning from the call, you would pretty much produce your procedure table, and you'd be guaranteed that your applications, procedures would be called. Now, those of you who may have been working in the Unix and Linux environment would know that in order to achieve that in Linux, you'd pretty much need to have any type of a kernel module inside the Linux kernel, for example, or any type of streams interface in Solaris, which would, of course, be a lot of hassle. But when it comes to Windows, all this is pretty much transparent to you. So, looking over the SPI CPP, which is the main file that has all the functions, let's just go over WSP startup briefly. And you'll see that what Intel and Microsoft do here, this is, again, their demo, is that they simply implement this WSP startup call. The important thing here would be, after initializing their own internal structure, would be, number 1, to save the Winsock2 upcall table. That is to say, save the actual implementations that are already out there, because we're going to need to call them as sort of a pass-through. And once that's done, they do a lot of other startup code and so forth, and they get to the important portion of populating the procedure table. So the procedure table is a structure, and it's as simple as it can get, because you'd have a structure of function pointers, and all you have to do is just hook your function pointer to the corresponding functionality that you want. And so once that's done, you can essentially hook all those calls. Now, just looking at one of those calls, say, for example, WSP receive, which would be the counterpart of the WSA receive and so forth. Okay, so looking through that, at some point we'll get there. Yeah, okay, there it is. So this is the WSP receive function, which is again guaranteed to be called prior to the application actually getting any data. So if Google, for example, wants to rewrite the content, this is exactly the function they'll hook. Now, again, I won't go over the numerous parameters here. The parameters of interest are obviously the socket in question. and a long pointer to the buffers. This would be an array of input buffers, and since we're passing an array by reference, we also have to piggyback the third parameter, which is the count of buffers, namely what is the size of said array. And so what I do in my little demo here is do a fairly simple function here, which would just go on and write to the debug file that it's intercepted a receive, and would simply go over the buffer. It's going over the entire array there, and simply printing out the buffers. Now, as far as a demo is concerned, this is really not the type of graphical pyrotechnic demo you'd imagine, because it also will intercept a lot of binary data. However, it does illustrate the point that the data can be intercepted and can be, of course, modified. If you want to, you can pretty much have any type of modification of those LP buffers, and you can inject your own buffers, you can put your data, you can log the data, and so forth. I, of course, chose just to log the data. Now, naturally, you do the same thing for WSP send and a host of other functions, but that goes without saying. So, we have our DLL, and now the next step would be to insert it. Okay, somehow get Winsock to recognize our service provider as a valid service provider. Now, bear in mind that this is something that has to be done outside the DLL, because your DLL can only intercept certain functions, but it cannot install itself. However, in order to install it, we have another call, which is a WC install provider. This is a fairly simple call, where all you have to do is provide a global unique identifier, which is, of course, easy to just whip up for yourself. And you'd set up your own DLL path and the type of protocols you support. That's all it takes. Now, your example should have, actually, I'll go to my source code here, just to demonstrate how simple it is. So all you'd have to do is have a small executable file, like, say, this inst LSP, which, again, is a verbatim copy of the Intel one. I didn't really do anything here, because this is the same generic code that would work with any service provider. And so what it does here is that it has a little function called install my provider, wherein I populate the provider info, like so. I populate a lot of stuff. You'll also notice a nice little flag here called PFL hidden, which is this flag right here, which is a really nice flag because this actually tells Winsock if anybody wants to enumerate this provider from the API level, keep it hidden. Which, I don't really get the actual intended use of that, but whatever. Now, there's also another interesting copy here, which is security scheme, which enables you to have your own type of security for your provider, blah, blah, blah. Most of the time, you just do protocol none. So, essentially, I populate this provider, and I, of course, register it as a protocol provider for TCP. And once that's done, all I have to do is just call this WC install provider and provide the name of LSP DLL. This is assumed to be in Windows system, which would be a problem if you're not an admin, but then again, you're going to have to be an admin to run this anyway. But you can also specify a full path here if you really want to. And so I load the protocol info through the pointer, and once that's done, I pretty much guaranteed that my provider will be installed there. Now, let's go ahead and try and install that provider and see exactly what happens. Now, you'll notice that I already took the liberty of placing that little DLL here. That DLL is as compact as 81K. Actually, it's 80K or so. And the thing is, once that DLL is in place, all I have to do is call the inst LSP executable to do the rest. Now, before I do that, I want to fire up Regmon. Regmon is a tool by sysinternals, which I'm sure most of you know, and that enables us to hook all types of registry calls. And the important thing here is that this type of functionality of installing providers or deinstalling providers is essentially all registry-based. So if you really want to bypass this type of DLL with enumerating the provider order and so forth, or installing your own providers, all you have to do is directly access the registry, which is, of course, fairly simple. So what I'm going to do now is I'm going to launch Regmon, and naturally all is silent because my process hasn't started yet. And now I'm going to run this inst LSP, and as I do, you can see that it's scanning the install providers and then going on to install my provider on top of all the rest. Now, again, since this is a rather crude demo, I didn't really go to any, pains of just looking for the right providers. I just said go ahead and install it over all the providers. But it's fairly simple to just decide that you want a very specific provider. Now, you can also see that there's a lot of registry action here, and specifically, all the registry action is focused on one specific branch, which is HQ local machine system, current control sets, services, and Winsock 2. So firing up regedit, just to see what it's like there, you'll see, and it's already in my favorites, you'll see that Winsock 2 parameters has the namespace catalog, which is for the namespace providers, and the protocol catalog, which is for the transport providers. Now again, Microsoft is inconsistent. They don't really call the things by the same name all the time, but that's, beside the point here. So, under the namespaces, you have all types of catalog entries, and as you can see, you have the same catalog entries that we could have seen under the SP order executable, namely the NTDS, the plain TCP/IP, and so forth. And when it comes to the protocol catalog here, everything gets really messy, because one would think that you'd get these nice type of keys and values, but here you only have a packed catalog item, which is a blob of binary data that if you go into, you'll actually see makes a lot of sense. This is a protocol info structure that has been overlain into the registry as raw binary data. Now you'll also note that once I put in my layered service provider, the number of providers here has risen from the 30-something that it should be to around 57, because that's where mine is hooking. So with all that in mind, the stage is set, and I can now run any application of my choice, as I'll shortly do. And you'll see that as the applications run, I'll get a nice little message box, and I'll get a full log of whatever. Any questions thus far? Yeah. Mm-hmm. Well, no, that would go with the namespace provider with the TCP/IP one, which I'm not really discussing how to hook that. If you really wanted to, you could also hook the loopback address as well, so as people would, go ahead and try to resolve and get the 127.0.0.1 because it's in your host file, but then the application would get that first. So you'd be able to actually rewrite the result of the NS lookup or whatever DNS packet should have been there, and you'd be able to just put in any address of your own, which is, of course, very nice for our purposes. Furthermore, the Google desktop would then have to connect to the loopback interface, and that would be a transport type action, and you'd be able to get the connect. You'd be able to hook the connect call and see a connect to 127.0.0.1 to whatever port Google is using, and of course redirect it. So simply providing your workaround wouldn't really work because this functionality is actually stronger than that. Any other questions? Yeah, back there. Say what? Oh, you can't. The beauty of it, okay, so the question is, say I want to put in my own provider. How can I ensure that my provider is the topmost? In 2 words, you can't. Because any provider that gets installed after you can pretty much rewrite the stack as they see fit. So you'd have the protocol chain, you think you're there first, but the whole beauty of this mechanism is that it's so transparent that at any other point in time somebody can get ahead, sort of like bump in front of you and hook you as well. So that's, of course, good news or bad news depending on your perspective here. Yeah, but that's not to guarantee that somebody else, some other application starting up after you, they could enumerate the order as well, and they could rewrite the order as they see fit. So essentially, this is somewhat of a limbo in the sense that you have a given order, but the enum protocols will only provide you with a snapshot of the current order and no guarantee of any other application coming after you. You cannot decide you want to be the topmost protocol in the chain, and that's it. Further, when any other protocol gets bumped in, you wouldn't know. You have no indication whatsoever as to your position. Yeah, you'd still be, well, again, okay, so... Right, okay, so the question is, would I still be hooked? And the answer is yes and no, because yes, I would be hooked in the sense that I'd have my own place in the protocol chain. I don't mind the fish. So I'll have my own place in the protocol chain, yes, but if any other topmost provider would want to hold that call in the chain and not propagate it, not play by the rules, they'd be able to intercept it and essentially block it. So as I place my own provider, I can either choose to go ahead and forward the call, or I can say, no, I want to handle the call and I don't want to propagate it further. You can change the providers at any time, okay? Using the provider order, the WSP right provider and so forth, you can pretty much redo the whole ordering as you wish, because essentially all it changes is some internal structure in Winsock. So, oh yeah, of course, but then again, there's no guarantee that you will be called again, because again, let's assume for a sake that I have my own custom provider, and I want to make sure that nobody gets on top of me. So, assuming whoever gets on top of me does forward the call further, yes, I will be called. But if that somebody takes the express route and just, decides to bypass whatever other calls, then essentially my provider would still be there but would never be called. Yeah, the order is in the registry, and of course in enum protocols would work as well. You could enum the protocol so as to get it in a nice little array. But the order is right here. Okay, this is pretty much the order. I mean, you can pretty much see that the key names are the ordinals, so it doesn't get too more complex than that. Last question? The root by sysinternals, I'm not familiar with the specific one, but I can tell you that a lot of other rootkit detectors don't really go that far. Now, it's important to just define the terms here. This is perfect user mode action. This is not a rootkit in the sense of like a kernel mode rootkit, because that would be hijacking TCP/IP.sys itself. And that, that there's nothing that can be done against that. But the beauty of it is that this is full user mode, and in that sense it's a lot easier, and not to mention you can code sloppy and not risk a blue screen of death, which is of course a nice little added benefit there. Okay, so since I'm getting the noose, I'll just run a few applications here. So let's just, let's just run Firefox and a bunch of others. Oh, and as you can see, Firefox is loading, and already I have a sock debug of 1148, which is of course the process ID of Firefox. So Firefox is running, and this is the Mozilla start page, and I can do all sorts of, other whatever. And see, I can get any types of pages I want, and everything is really nice and dandy. But behind the scenes, I have this little sock debug 1148. And of course, I could also fire up my Messenger or my Yahoo or whatever, and I'll do that just briefly here. So as I fire up Yahoo, I should be getting the message box sometime soon. Yeah, just, Yahoo's a bit slow. Okay, now you'll notice this is a really nice effect that I get the message box in the context of the Yahoo process, so I get their window class, which is a nice, not really nice, but purple, whatever. Okay, and so this is connecting and everything is cool and nice. You can also see that it's hooking another call, and whatever, they'll just let it run. And, ditto for Messenger. So if I'll just run here, run Messenger, yeah, whatever. Yeah, you can. Okay, whatever. That's a student of mine. Disregard that. Okay? So, again, so I can run that with Messenger and so forth. And all these sock debug files are right here. So let's just go over the 1148 one. And you'll be able to see that, again, this is very crude. So I get a lot of seemingly junk-looking data. This junk-looking data is all types of either gzip compressed HTTP data or all sorts of binary data, such as images and so forth. If I scroll down, I should be able to see some HTTP requests right here. Okay, so this is the get of header tab.gif, and naturally you get all types of this. This, for example, is a PNG. You can pretty much see the header here. That's a dead giveaway, as well as a bunch of others, etc., etc. The HTTP replies and so forth. Now again, I want to emphasize one thing. This, again, as a demo, is not as half as fancy as it can be. Because with a little if there, I could have simply rerouted Mozilla to some other site, or I could have modified whatever Mozilla was displaying. Now, another disclaimer here is that HTTPS type connections are unaffected by that. Fortunately, there are other ways to hook HTTPS, which are beyond my scope here. But I'm just saying that if you do use HTTPS, you're fine. However, when it comes to all types of other functionality, Messenger, email, whatever, everything is pretty much in the clear. Okay? Any questions? Yeah. Yeah, with NetBT you can, although it's, well, again, let's define NetBT. If the process that runs the NetBT request has launched after you have put in your provider, then yes, you can. And if you get your provider into the Windows startup, then yes, you can. Okay, however, some functionality you still won't get, namely the Winsock bypass functionality that sometimes a server service does. Okay, in order to gain efficiency, it doesn't go through a user mode DLL because it doesn't make sense, you know. Okay, so you can hijack some of the functionality, although not all. Any other questions? Yeah. No, Zone Alarm actually, as far as I know, go into the TDI. This is what McAfee does, though. McAfee, the personal firewall, they do that. So, but again, this is kind of like a paradox in the sense that it's absurd, because if McAfee uses that and I can pretty much intercept their calls and get on top or reroute them to the bottom, then it's really useless. Any further questions? Because I'm getting the sort of like Neustein. So yeah, right there. Okay, the question is, if I'm intercepting a WSP receive, if I'm intercepting an SSL socket, would it be encrypted or not? And yes, it would be encrypted because I'm essentially getting it as it came on the network. So this enables you to play middleman, but only middleman, post SSL or post encryption, which is, as I've stated, the proper workaround, the proper mitigation to that would be to always use SSL and so forth. However, bear in mind that nothing is preventing the application from also, trying to forge certificates and do any type of DSNF type man in the middle, which would work here. Okay, so just to conclude before I'm kicked out violently. Okay, so that was the demo. The lesson to be learned, the thing you need to carry home from this, is that no matter what you do, no matter how you code your application, the beauty of Winsock is in transparency. However, this is a double-edged sword, because obviously, as transparent as it is, it enables attackers to subvert either client sockets, server sockets, whatever. Now, it's also important to emphasize that this was originally intended for good uses. Namely, implementing an application type firewall, application layer firewall. We mentioned McAfee, and of course, we saw where that got. Transparently add encryption. This was well before the days of IPsec. We're talking about 98, before IPsec was a fully robust protocol, as it is now. And nowadays, IPsec is handled, of course, in the kernel level. Enforce quality of service. Yeah, right. Support new protocols. This is also another nifty functionality. You can essentially support IPv6 by it, although it's supported already. You can support IPv9. You can support pretty much any other custom protocol over a raw socket. And patch content on the fly, which, like I said, Google Desktop actually do. Whether it's a legitimate use or an illegitimate use remains to be seen. However, the much better chaotic uses would be to patch content on the fly in the illegitimate sense. And again, we're talking about rewriting web pages, rewriting IMs, doing a lot of other nifty stuff, which I will not disclose here. Obtain connection statistics, URLs, etc., etc. Most of the spyware applications do exactly that. They put themselves in so as to gather your statistics. This was what the Kazaa spyware did. Eavesdropping on any type of connection, but again, non-SSL ones. And rerouting connections, that is just hijacking the sockets, which is really an amazing thing, because an application opens a socket and calls connect. And once it does that, then the worst that can happen is it's going to call get peer adder. But you can reroute connect, and you can also reroute get peer adders. So whatever the application thinks it's doing, wherever it's actually thinking that it's connecting to, it has no real significance here, because you can do whatever you want with it. So, all that in mind, the demo, like I said, is part of the platform SDK. You're welcome to drop a line to this address right here. And if you need, you know, the demo with the actual explanation on what I did, where I did, and so forth, then it will be supplied, of course. Any further questions? Okay.